Today on the Skid Factory, we're talking turbos. We've been meaning to talk about this for quite a while, but we've been too busy building cars, so we thought we'd spare half an hour and talk about turbos. I've just dug a heap of turbos out of my junk pile of turbos, just some different types. Obviously they vary quite a lot in both size and design, so we'll just sort of run through a few common variances, more focusing on the stuff that you can buy aftermarket, I guess, but we'll also explain a few differences. We've got twin entry, single entry, twin scroll, which isn't the same as twin entry, internal wastegate, external wastegate, and also a VNT, so variable nozzle. We probably should start with the basics. How does it work and what does it do? I might use this broken GT35 for that because it's already pulled apart. So we've got two sides, turbine and compressor, and the core in the middle that supports it. So this particular turbo is a ball bearing, which is one of the ways that they can support the shaft. There's ball and journal bearing, which is like a floating brass slipper bearing. I won't go into that because it's kind of long-winded. So what a turbo is it's a turbine-powered supercharger, so turbocharger for short. This is the turbine. That is powered by exhaust gas. It makes the turbo spin. This is the compressor. It then moves the air that goes into the engine. So without the turbine, without the right turbine, this doesn't work. They have to be matched. They have to be matched in turbine flow and compressor flow, and also have to be matched to the engine. Huge variances. You know, you can't put a tiny turbine on a big compressor because it just physically will not be able to drive it. There's huge load on both of them. The compressor actually is under a massive load moving the air. So for it to move it, it has to have drive. So that's the drive, that's the compressor. If you were to look at this and pretend it's like a centrifugal supercharger, that would just be driven by the crankshaft instead. So same sort of thing. This is a centrifugal compressor. It's just driven by a turbine. So it's using waste energy to drive it rather than using crankshaft energy. So it is better by a long shot and in many ways, but I won't go into that. So the compressor is very important. It's obviously what moves the air into the engine, and it has to be efficient at doing that, but it won't do anything unless it's driven properly by the turbine. So the turbine is, to me, the most important part of the turbo. You have to get its size right, and you have to get the housing that goes around its size right. Otherwise, the engine will not operate correctly. So don't dwell on the compressor. Start with the turbine when you're choosing a turbo. It has to be correct, otherwise this won't work. So let's have a look at some turbine housing designs. This is a Japanese IHI turbo, and this is what we call twin scroll. So twin scroll and twin entry aren't really the same thing. A twin scroll actually has two scrolls. So if you talk about that being the scroll around the turbine itself, you'll see there's one large one and one small one, and they operate on different points on the blade. I don't know who designed this, or I've only really seen it on Japanese turbos, so I guess it's something to do with them. Different to twin entry, this is a Garrett GT40. you can see it does have twin passages, but they aren't separately sized and they don't contact the blades in separate spots. It's just, this is like a pulse tuning, widely used on 6-cylinder trucks. That's its origin. Basically, front 3 cylinders, rear 3 cylinders into the separate passages, meet in the middle, drive the turbine. Works great on 6-cylinder petrol engines, V8s if you're using one per side. 4 cylinders also, yeah. Hard to get a turbo like this to work on a 4-cylinder because it's too big anyway. But yeah, it is a good idea. Anywhere above GT35, right up until you get to the really big stuff where they change back to single entry, most of the time they're going to be twin entry turbos just because they're based on truck turbos. So that's why they've always got twin entry housings on them. Some turbos do have single entry, but it's more common for them to be twin in this size frame. Whereas below that, it's more common to be single entry, like on a GT35. So that's your single entry, pretty self-explanatory. It's got one hole going into it, one sort of point where it contacts the turbine. So what happens is, exhaust gas comes in and it gets slowly squashed down into the nozzle. And the nozzle is the part where it contacts the major side of the blade, so the larger side of the turbine. You can see the turbine's bigger there than it is here. So that's your exit point on the smaller side. That's the entry point there. So what we're doing is hot gas, keeping it hot, pushing it down into a nozzle and basically spraying it onto that blade. So it's got a lot of energy concentrated. It then, it's released into sort of a more open area and it expands across that blade point there, and that creates rotation, and then multiply that by a lot. So that's where your drive comes from. The differences in housing is just trying to make a more efficient drive or making that drive for the turbine match the engine's characteristics. So that's why there's all these different ways of doing it. One variation from this theme is a variable nozzle turbo. So these are used on diesels. Very odd. I think it's a Porsche that uses them on a petrol engine, but basically it's pretty much diesel specific. So there we got the turbine, and instead of having a scroll for a housing, it's a pretty flat, straight, ordinary looking thing with no nozzle to speak of. So it doesn't taper down to a point where it drives the turbine. Instead, it's got heaps of nozzles, and they're controlled with these little levers here. So it's incredibly complicated mechanically. It's not very complicated to control from the outside, but all these little levers, they've got a pivot points that have got to deal with heat, and that's why they're not really used on petrol engines, because the exhaust gas temperature on petrol engines is much higher than a diesel engine. So I'll show you the inside there. You can see that nozzle opening and shutting. So basically I want all the boost, it's pointing it directly at the turbine. I want less boost, well, not less boost, I want less drive because I'm already at my required turbine speed. So drive the turbine to speed really fast and then open back up. So it still drives, but it doesn't need to go any faster than it already is because we've already reached our boost pressure that we want. So complicated. Yes, it works. Yes, it can give you instant boost pressure, but instant boost pressure doesn't make the engine more powerful without fuel, all those other things. Personally, my theory is that they use this so they can have absolute control over boost pressure at any time, part of the RPM range on a diesel engine, because when they want to enable EGR, like exhaust gas recirculation, they have to reduce the boost pressure to allow the exhaust gas to enter. So the boost pressure has got to be lower than the exhaust manifold pressure. So they can control it with this at any point. So they just open up the vane and lower the boost pressure, allows the exhaust gas to go in. I've taken probably this exact turbo off a car and replaced it with a normal turbo, and it made absolutely no difference to the response or anything on the engine. It worked exactly the same. So they're not adding this complexity for no reason, and the only reason I can see is for other purposes, as in emission control. And that is often the case in a lot of technology. It's not there to make the car go better, it's there to make it be controllable for emissions purposes, because they've got to sell the cars and they're not allowed to if they don't pass. So always something to keep in mind when you see technology, is to think, why is it there? It's usually not to make the car go better. So we'll disregard them. There's the little control lever there. It's usually got either a diaphragm, or sometimes they got like a computer control, like a stepper motor, which invariably breaks way ahead of time and costs thousands of dollars. So not great. There for a purpose. We don't really care. So on that theme of controlling the turbine speed, wastegates, that's what they're for. Turbine speed equals boost pressure, because the turbine's driving the centrifugal compressor and it makes boost pressure with speed. So it's not like a roots blower or whatever that displaces this much air every time it turns, like a 1471 or whatever you want to see on the front of a bloody power cruise car. The compressor, that compressor works better as it gets faster, to a point where it then starts heating the air. So to control the boost pressure, you control the turbine speed at the right point. That boost pressure is obviously going to change. If the engine's bigger, it's not going to make the same boost as if it was smaller with that same speed. So very dynamic system. You've got to, you can't apply every rule exactly the same. The engine changing the engine's airflow characteristics by putting a different camshaft in it, making the engine more efficient, will make the boost lower, because boost pressure is it's a restriction in the engine. If there's no restriction in the engine, you won't get any boost, but you still get the same airflow. So very dynamic. You've got to use an open mind when you're talking about turbocharging. So back to control of the turbine speed. I'm rambling. Wastegates. So this is an internal wastegate. Basically, it's just got a little flap that opens up. All the gas going through the turbine, some of it not going through it. That would float around like this to keep the speed of the turbine right. So it's sort of a closed loop system, and that would keep the turbine at the right speed to make the boost pressure correct for the specific engine it's on. So obviously you have something like a diaphragm like that on there with a set spring pressure, floats around, controls this turbine speed. This turbo doesn't have an internal wastegate. That's called a free float housing. So basically that turbo will make as much boost as the engine as a system can make if you leave it like that. And that's what they used to do to trucks. They never had wastegates on them because they didn't need to, because they were low revving engines. They were all set specifically for fueling and that sort of thing. So they just let the turbo make as much boost. And without fuel, the engine They just controlled the engine's characteristics with fuel. So the turbo won't make more boost unless it's got engine efficiency, and they didn't need a wastegate. Modern trucks usually do have wastegates now. Maybe not so the very large truck engines, but the smaller ones do, for whatever reason. And a lot of them have got also variable vane on them for emissions purposes. So when you're using this sort of housing in a vehicle, like a petrol engine application, you've got to wastegate it, otherwise it's just going to go through the roof and you're going to blow the top off your engine. So that's an external wastegate, EX44 GFB in this case. It uses a poppet valve, similar to what you have in the top end of your engine if it's not a rotary. That's what I call a swing valve or a gate valve. See, it swings open like that. This particular valve, it opens up that way. It's got a heavy spring in it, so I can't push it open. But basically, what they're doing is bypassing gas from going through over the top of the turbine and powering it to just going out the exhaust. So that's how you control the speed. Some drag cars have tried using no wastegate and controlling the boost pressure by just dumping it out of valves. That would also work, but obviously completely impractical for a road car. And it also makes the turbo do way more work than it should. You're still making the boost pressure, you're still driving everything, wearing everything, and then dumping it before it gets to the engine. That's completely impractical. Except for an application of maybe a drag car where you just don't care and the engine's probably only going to last one pass anyway. So, housings, even more technical. We've got turbine size, but then we've also got housing size. So, this is a GT35, and so is this. Albeit that's a Chinese copy, but it's the same outline, interchangeable. It's exactly the same otherwise. So we'll try and get the camera to see this, but this is a 0.8 housing and this is a 106 housing. So they both fit in the same place. Obviously that's internal gate, so it's got a different outlet flange on it, but if you can see how large this housing is compared to that, that's another way of fine-tuning how the turbine is driven. And basically what you're getting here is more response. It's going to bring the turbo on, going to bring the turbine up to speed faster, which brings it on boost quicker. And this one is going to be slower because it's a larger volume inside there. The payoff is this one's going to make more power because it's going to allow the engine to breathe exhaust gas through it more efficiently when the engine is actually making power, whereas this one's going to restrict it eventually. So you can't just put a smaller turbine or a smaller exhaust housing on and go, yay, I've won, I've got more response, because all you're doing is choking the engine. The engine still has to operate as an air pump. It still has to vacate its exhaust gases, otherwise it won't make power. So you can't have it all. You can't put a tiny housing on an engine and go, I've fixed it, I've put a wastegate on it that's really big. That doesn't work either. It just doesn't work that way. It's been done in the past and people claim it works, but it just doesn't. So you've got to have the right size turbine housing to go with your application. If you put a bigger one on it, it will make more power, it will be laggier, end of story. So choosing the housing size and the housing type is also another thing you've got to go through before you choose your compressor. So keep that in mind. You've got to have the drive for the compressor to work. So after you've chosen those things, then you can choose your compressor size, because you can actually, particularly in Garrett, you can have on a GT35, you can have a 3582, or you can have a 3576, which is obviously quite a bit smaller. When you start getting into the billet compressors, GDXs, there's 76 mil, there's 82 mil, there's 84 mil. A lot of variations. You've got to pick the compressor to go with your engine's airflow characteristics, but also understand that there's payoffs with everything. You can't just go, I'm just going to put the biggest compressor on, because it'll make it laggier. The compressor takes more energy to drive, it's going to be laggier. So if you only need a 76 mil compressor to achieve your power output, whatever it's rated to, then just use a 76 mil, because if you put an 82 mil on it, it's just going to be laggier and you're going to make the same power. So you've got to keep in sight what you're trying to achieve when you choose a turbo. So I'll briefly go into billet compressors. What does a billet compressor to do? Not much, it just makes it easier to manufacture. The only way they get, the advantage of them is, I'll use this turbo. The advantage of a billet compressor is mainly that they can finely machine this down to, and basically they're just increasing blade area. So even though it's the same size, it's actually got more volume, it can pass more air volume. So technically it's bigger, and you've got to keep that in mind. So if you get say a GDX 3582, that compressor is bigger than the GT 3582, even though they've got the same external size. Therefore, you need the turbine to be able to drive that compressor. So again, you should put a bigger exhaust housing on that turbine, or say in the case of the GDX 3584 RS, that has an even bigger compressor again. So what you need with that is, it's got actually one less blade on the turbine. So how Garrett's dealt with it is, they've kind of made this less efficient by removing one of the blades, but that also unshrouds it and allows the exhaust gas to flow. And then of course you can choose your housings. I tend to choose bigger housings now. The turbos just work better, and the couple of hundred RPM difference, or 500 at the most, between a 106 and a 0.82, you'll get that back tenfold just by being able to put more ignition timing in, because the engine is not choking on the housing. Then of course you've got E85 and all that allows you to make the engine more efficient overall. So I prefer bigger housings. The turbos just work better. So I just go with what I've experienced. I could go on for hours about this. It's a very broad topic. There's a lot of variations. The biggest variation with turbochargers is the engine they're bolted to. You have to match it to your engine. So please don't message us asking what sort of turbo to put on your STI. Just Google it. It's all been done before. Use your brain. If you're doing custom setup, you have to work it out. So understand how a turbo works, understand what it needs to operate, and go from there. Ball bearing, journal bearing, it doesn't make any difference to the way the turbo moves air. A ball bearing turbo, the ball bearings are there not to make the thing spin easy or anything like that. It's just that they will control shaft movement much more accurately and reliably than a journal bearing turbo will. Although journal bearing turbos have come so far in the last 20 years that there's virtually no difference now anyway. So get out there and turbo your cars. Thanks for watching. This is buggered because it's off a Ford. Now what? Is it like 50 minutes because I'm parched?